Hello there. In this video, we're going to move on to our third tutorial using the Q package. In this case, we're going to talk about something called restricted networks, and for this video, we're going to be following the documentation. So let's dive in. Imagine a manufacturing plant that produces stools. I assume this is the kind of stools that you sit on. So every 4 seconds, a seat arrives on a conveyor belt. So this is describing our arrival process of something that's coming into the system overall. The belt contains 3 workstations. Okay, that might be nodes, but we don't know yet. At each workstation, a leg is connected. So this is telling us that there's some kind of task being done at the workstation. So even if we weren't following a tutorial, this is a very plausible candidate for making into a node with Q. Now, next piece is connecting a leg takes a random amount of time between 3 seconds and 5 seconds. This is an ongoing theme with the documentation that I'm seeing with Q, is that it just kind of says at random, but then later on it's going to assume particular probability distributions. There are a ton of different distributions, and we would consider the vast majority of them random, except for what's called the deterministic function in Q, or what I would describe in mathematical terms as like a Dirac delta distribution or other such things. Anyway, enough rambling about that. It's just to say we're going to have to take a particular interpretation of what this means, and that there are different ways of interpreting the information that is given to us when we're actually taking in business requirements. Now, between workstations and before the first workstation, the conveyor belt is only long enough to hold 3 stools. So now we're talking about something that is new compared to the tutorials that we've already covered. The tutorials we covered so far have assumed that you can have really just any number of customers, or in this case, we're going to change from customers to talking about stools, chairs, legs. I guess we're talking about the chairs without legs arriving or something like that. What is it? A seat arrives every whatever seconds. Okay. Yeah, seats that are going to have legs put on them. Okay. If the belt before the workstation is full, then new stools fall to the floor and break. So that's telling us about what happens in the situation of going, okay, well, you can have that arrival rate as we defined above, but what happens in the situation, which may occur with some non-zero probability, that we already have maximum capacity of the chairs, the seats, and so you can't add more. Here they're saying they're basically removed. This is sometimes called blocking, which we'll come back to. And by the way, one of the things maybe we could come back to in a different video is to expand on this example to go, what if we need both stools, both the legs and the seats to have separate arrival processes? Here it just sounds like we're assuming that there's always legs available to put on the seats whenever the seats arrive. But in a more general process, you may have to consider both things arriving in order for some kind of service to happen. We'll come back to that some other time, or at least I think that that's a reasonable topic to come back to. So, if a stool finishes service at a workstation, but there is no space on the conveyor belt, that stool must remain at the workstation until room becomes available on the conveyor belt. While this blockage happens, that workstation cannot begin assembling any more stools. And it gives a link to more of the information on blocking. We're not going to read that right now. That's elsewhere in the docs, and maybe we'll get to reading that later. Okay, so each broken stool costs the factory 10 pieces. I assume that's pieces in wasted wood. Otherwise, I'm not sure what the unit P means. Yeah, it must be pieces. We wish to know how many stools fall to the floor and break per hour of operation. So we're looking at computing the amount of waste, and thus the average cost per hour associated with that waste. First, let's define a network. The network for this problem. Maybe I should say a network, because it's, there's different ways you could model the same problem. A restricted network such as this is represented by nearly the same network object as the unrestricted cases, which are the cases we've seen up until now. But now we include the keyword Q capacities. I see in the text here that it's capital Q, but actually for the parameters inputting a following conventional snake casing, it's going to be Q capacities all small case. Okay, so let's put that documentation to the side, and we will create, this is tutorial 3. So the first thing that we'll put at the top is importing the library. Next, we'll define a network, and we'll go Q create network. And we're going to start putting in first our arrival distributions as a list. And we've got the first one is q.dists.uniform. Lower is equal to 3. Upper is equal to 5. And that makes sense because we're saying that there are these multiple stations that have these arrival rates. So we'll put that in and we'll duplicate those. They are all the same? Yes, good. That's what I was hoping, expecting. Okay. Then the service distributions. So how quickly each of the sites are supplying the service. Ooh, no. Whoops. No, I misread stuff. So this is our service distributions, and we will go back up here to define our arrivals. That's right. Arrival distributions. So there's only one place that they arrive from that conveyor belt, and they are arriving at fixed intervals, perfectly fixed, which is not very realistic for a lot of problems, but we're going to do it. And actually, I'm going to put that on another line as well. And then nothing arrives at these other nodes. Now we can finish up with the services. Got it, hopefully. And let's write the routing of basically where things are going in the network. So if we're at the first node, it does not come back to the same node. It will, with 100% probability, go to the second node, and there's no chance of it going to the third node. The next node is all, whoops, is not all, but is, excuse me, at the second node, with 100% probability, you will go to the third node. So it's a production line type of thing. And then the last one, you can just write times 3 there. And that's our routing. So by the time you're at the third node, you have a 100% chance of that thing leaving the network simulation. Okay. And now we got number of services. And that is equal to 1 for all of them. So we'll just go 1 times this is just a little bit of Python syntax sugar. We could actually just be explicit here. And instead of duplicating the list that way, we can just put 1s. Q capacities. So this is the new part for us. This is that every one of these nodes can only have a maximum of 3 at any given time at the network. And just to make sure that we're good with, no, we are not. Command not found. Oh, this is an environment thing. Did it to myself again. Oops. 3. Let's try again. Python tutorial 3. So we got, oh yes. So I made a typo here. Number of servers. There we go. Good. So we've defined this network, and the key thing that we've put in that's new is this queue capacities, that there's a maximum of 3 that can be at the queue at once. Otherwise, they get blocked. So in this production line, we want to calculate something like the waste, right? That's what the tutorial said. So let's see what it gets onto with the next thing. Oh, it's calculating blockages, right? The time taken to attach a leg to the stool, service time, is sampled using the uniform distribution. Yeah, we saw that. And that makes some assumptions. I guess that's also a maximum entropy distribution given that finite interval support. So that's not entirely unreasonable. It's the most kind of spread out, flattened distribution possible. This samples values equally likely between an upper and lower limit. Sure. Note the time units here are in seconds. Okay. I mean, they're basically telling us that because otherwise we would have to put it together with context. There's no explicit computing or a data structure for like units or something here. It's just you have to know what the unit is that you've chosen as the base unit for your simulation. So if we simulate this, we have access to information about the blockages. For example, the amount of time a stool was spent blocked at each node. To illustrate, let's simulate for 20 minutes. Okay, so let's let's follow along with the code there. So let's say q.seed, and they're using a seed of 1. We'll define our simulation instance, simulation, and we will put in our network, and then we will go simulation dot, and we will simulate until the maximum time of, they want to do 1200. That's just what 20 minutes is, because our base unit is in seconds here. And then we'll say records, and we will go simulation and get all records. And the next thing that they'll do is calculate the blockages. Well, we'll extract them first of all, and that involves taking each record. So we'll go record time blocked, and we'll go grab all of them that meet that requirement. Time blocked for record in records, and they print the maximum. I kind of just want to check out what the blockages are first. So let's take a little peek at that. And you can see that there's a bunch of zeros and there's a few non-zeros. And oh, interesting that there's not a number. I'm assuming, I shouldn't assume what that means. I should look up later what a none type is. And this is one of the reasons why it's good to probably check what's going on with data structures that you've got, right? Let's also, sure, print the maximum of the blockages. So the maximum that we got is the same, which we should expect because we're using the same seed number and simulation config. So 1.4 seconds is the maximum amount of blockage time. Okay, so here we see that in 20 minutes, the maximum time a stool was blocked at a workstation for was 1.4 seconds, is what the doc says. It's kind of right, but it's only right for that particular seed number, and that's one of the reasons why we usually want to do the same simulation multiple times under some kind of assumption that our sampling process is representative of the true data generating process that we want to model. But for this particular simulation, it's not unfactual. It just means if I put in 20 minutes again, but ran it with a different seed, a different arbitrary number that initializes the random pseudo-random number generators, we would very plausibly get a different answer. Okay, moving on. The stools that fell, there's a typo there, off the conveyor belt are also recorded. These are rejected customers, and so we can look at the data records of type rejection. So those were stopped from, those are instances in time where somebody attempted to move and was rejected from moving onto the conveyor. Oh wait, no, I'm wrong. No, rejected, sorry, is when they got kicked off of the conveyor belt. Okay, let's take a look at that. Rejected stools. So we've got list comprehension, record for record in records, and then we're doing some conditional stuff inside here of going records, and we're really just trying to filter out for the specific type of record rejection. Quick look at that. Check stools. And we can see the records where the type was of type rejected. Can I see that? Yeah, I see the bottom one. See at the very end there, record type equals rejection. So that looks good. We can also, amongst these rejected stools, we can take a look at the arrival times. So if I go another, do I want to create another variable or just want to print? I guess I'll just print. But I'll stick it in here. So let's print record.arrival date for record in rejected stools. And we can see the same two records that they provided. One of the arrival times was at 1020 seconds and the other one was at 1184 seconds. Good. Now, you should think at a quick glance for floating numbers with time in simulations that it's not necessarily wrong or bad if you see zeros, right? Like in the simulation, I'm seeing 1200.0 and 0.0, and that can be a warning sign, but it's not necessarily bad. In this case, it's not bad at all because in this simulation, we had the deterministic arrival times, right? Up here, deterministic of every 4 seconds. And so the other thing we could check, which I'm not going to formally, but you can check for yourself that you can divide both of those numbers by 4. So that should be what we expect since we started the initial time at 0. It's good to do little checks. Sometimes they're called sanity checks, but they're just little checks to make sure that stuff makes sense. What you're looking at makes sense. Informal validation can be helpful, although formal validation methods are also quite helpful. Different purposes. Okay, so let's get back to reading this little bit of the docs here. Now we'll run 8 trials and get, oh no, I skipped ahead. In this run, 2 stools were rejected, fell to the floor as there was no room on the conveyor belt at node 1 at times 1020 and 1184. To get the number of stools rejected, take the length of the list. Sure. We could calculate that. I don't think we need to calculate just taking the length of that list. We can see with our eyeballs that it was 2. Okay, now let's run 8 trials and get the average number of rejections in an hour. We will take a warm-up of 10 minutes. A cool-down will be unnecessary as we are recording rejections, which happen at time of arrival. So there's no censoring effects of like an incomplete arrival or something. The arrivals are instantaneous. They happen at specific moments in time, and the event we're interested in is exactly when those arrival events occur. And we want to know what are the arrival rates that are getting rejected, basically. Okay, so let's keep the rejected stools, but we will drop that other piece. Okay, so let's turn this into our familiar kind of loop pattern. You could organize this differently, but we're going to just keep it simple for following the tutorials. But you may instead want to, well, getting ahead of myself, but there are some things you can do to parallelize these trials and whatnot. Okay, we'll put in the trial number. All of this is going to go inside the for loop. Our simulation object with our network, which we are reusing from above. We've got our simulation time, which now is 4,200 seconds. We're getting all of the records, and then we're getting the number that are broken. And just to make sure I'm getting the full list comprehension there. So, right, for the cooldown, we're not grabbing anything that came after. Oh, sorry, warm up. Right, it's after. Anything after 600 we're not keeping, so that's our 600 seconds of warm up. And we're only keeping records of type rejection. Okay, so let's go and grab, actually, let's start throwing this onto another line. If record dot record type is equal to rejection, and record dot arrival date is strictly greater than 600. And we can probably clean this up a little bit too. Maybe I'll put it in this format. We'll put the thing we're trying to get at the top, and then the loop, and then additional conditions, something like that. I don't know. We don't have to spend so much time on formatting. I just like to make these longer list comprehensions a little bit more readable, almost as if it was a for loop, but not quite, obviously. Okay, and then we need to collect our result. Oh, I forgot something. So they want to know the length. So let's put that in a length call. And now let's go broken stools append the number that were broken. And we're going to throw away this rejected stools. And at the end of doing all these trials, let's print the broken stools. Okay, so do we get the same numbers? We should, because we have the same seed. And look at that, we have the same numbers, 9, 10, 6, 9, 4, 7, 10, 3. Great. And then we might calculate that aforementioned average. So we'll do it with just pure Python here. We'll take the broken stools and divide by the length of the broken stools. And I did not close parenthesis, and we will also want to print. And there's our 7.25. That's the average. That is the average number of broken stools, which is great. I mean, I don't know that that number is great. I guess we want this number to be 0, but it's great that the simulation works. Next. So, on average, the system gets 7.25 broken stools per hour, costing an average of 72.5 p per hour of operation. So I think that p is some kind of currency. I am curious, what is the Welsh currency? Maybe it's like pence or pound sterling. I don't know. It's in pounds. Maybe it's pence. I don't know. I don't know the I should know because I've been out that way, but I actually don't know off the top of my head. Bit rusty memory. Okay. Anyway, a new stool assembly system costs 2,500 pounds, can reduce the variance in the leg assembly time such that it takes between 3.5 and 4.5 seconds to attach a leg. How many hours of operation will the manufacturing plant need to run for that so that the new system has saved the plant as much money as it costed? Okay, so I think that's an interesting and worthwhile question. I wonder if they've set up the example here to actually answer the question, or if it's just simulating the new system. Oh, it takes a ratio at the end and assumes that you can calculate a proportion like that. Okay, so perhaps what we'll do, I'm tempted to maybe create a separate file. I don't necessarily want to run both simulations every time I run this. But I think all of this stuff is basically the same, isn't it? We're just going to change the model. So, yes, that's right. These are going to be tightened up into a range of 3.5 to 4.5. What do I want to do? Guess I could just copy that whole thing, call this network 2, and we'll update one of these rows to 3.5 and this one to 4.5. We'll delete these, copy them. The rest of this stuff I assume is the same. If I was trying to keep this script as something that was like a nice reusable analysis, I might do a bunch more formatting, but that's okay for what I'm trying to get here. So there's our 8.75 with the updated service time distributions. And then finally, they look at taking the ratio there. So it says, thus the new system saves an average of 6.375 stools per hour, around 63.75 pence per hour, and therefore it would take 2,500 divided by 0.6375, approximately equal to 3,921.57 hours of operation for the system to begin paying off. And that's actually a really great kind of question to answer, is how much time will it take for something that is maybe more efficient to actually become worthwhile? If something is meant to exist indefinitely, truly indefinitely, then any amount of gain there is worthwhile because eventually you'll get benefits. But if there's some kind of short-term deadline that something needs to be better than by, then it may not be a given that it's worth doing. So some organizations work on kind of yearly fiscal periods, and that if something can't be demonstrated to be better within a year, then it becomes harder to justify that change. I'm not saying that it shouldn't be done, but you may have to make a case on why it doesn't appear to be better now. Okay, so with that example, just to recap on what the purpose of this example was, is to show you restricted networks. It got a little bit into scenario comparisons, which I think is great. And the main thing with restricted networks is the idea that the queue itself can only take so many at once. And so when something attempts to enter a queue, it can get rejected from that queue. And then the second part of doing some scenario analysis is to say that in the long run, something may be worth it, or there may be some amount of time before it becomes worth it, and that can have an impact on your decision making. Okay, with that, thank you for watching. Hopefully you got value out of looking at these examples with me, and I will see you in the next video.